Welcome to the Deep Dive. Today we're digging into a really interesting academic paper. It sits right at the intersection of AI and hardware design.
Yeah, it's fascinating stuff. We're looking at whether these powerful large language models, the LLMs everyone's talking about, can actually help with optimizing hardware.
Specifically, we're talking about high-level synthesis optimization, right? HLS.
Exactly. HLS is, well, it's the process where you take high-level code, think C++ or something similar,
Oh, okay.
and you automatically generate a hardware implementation from it, like a blueprint for a chip.
So instead of writing low-level hardware code, which is super complex, you write C++ and synthesize it.
That's the idea. But making that hardware good, efficient, fast, that's the tricky part. It often involves adding special instructions, pragmas.
Pragmas. I've heard of those. They're like hints for the synthesis tool.
Precisely. They guide the tool on how to balance things like speed, power usage, and how much space the design takes up on the silicon chip. It's a real balancing act.
And doing that well takes a lot of human expertise, I gather. Lots of trial and error.
Definitely. It's time-consuming, requires deep knowledge. So the core question this paper asks is, can these newer LLMs, especially the ones with enhanced reasoning skills, help automate this? Can they actually think about these hardware trade-offs?
The kind of reasoning they use for coding or math problems, but applied to hardware.
Exactly. The paper investigates this using what they call an agentic framework.
Okay, an agentic framework. Before we dive into that, what's the backstory here? Why look at LLMs for this now?
Well, hardware design keeps getting more complex. Think about modern chips, systems on a chip. They're incredibly dense.
Moore's law slowing down, need for custom accelerators.
Right, so automation is crucial. People have tried automating HLS optimization before using various algorithms, even early machine learning. But often these methods need to explore a huge number of possibilities, which takes ages.
They call that design space exploration, right? Sampling tons of options.
Yeah, and it can be computationally very expensive. So the idea here was maybe these LLMs, which have shown amazing results in understanding and generating software code, maybe they can be smarter about exploring this hardware design space.
A more intelligent guide rather than just brute force sampling.
That's the hope. Leverage their reasoning abilities, which have been hyped up quite a bit, especially with techniques like chain of thought.
Chain of thought, that's where the model explains its reasoning step by step.
The idea is it helps a model arrive at better conclusions for complex tasks. So the researchers built this framework, this agentic system.
Right, the agentic framework. Tell us about that. What does the LLM do in this system?
Okay, so think of the LLM as an active participant. It's not just passively generating text. It can actually rewrite the C++ code.
Really? Modify the source?
Yep. And it can insert those pragmas we talked about, strategically placing them to try and optimize the design.
Okay, so it makes changes. Then what?
Then, crucially, it gets feedback. It uses standard HLS tools to synthesize its proposed design into hardware.
So it sees the results of its actions.
Exactly. It gets back reports on the area the hardware uses, the latency, how fast it runs, and the throughput. And it even uses things like integer linear programming solvers.
ILP solvers, what are those for?
Think of it like a mathematical optimization tool. Given constraints, like a maximum chip area, it tries to find the best way to configure things to, say, minimize the latency. The LLM can try to formulate the problem for the ILP solver.
So the LLM uses code changes, pragmas, synthesis results, and this ILP thing to iteratively improve the design.
That's the core loop, yeah. Make a change, synthesize, get feedback, learn, try again.
And the paper tested this framework on specific tasks.
Right, two main tasks. First, they focused on the kernel level. That means optimizing individual functions within the code.
Like optimizing one specific job the hardware needs to do.
Exactly. The LM would try different pragmas, maybe small code tweaks, for just that one function. The goal was to generate a menu of options for that kernel, each with a different area versus performance trade-off.
So not just one best version, but several possibilities.
Yeah, a range of Pareto-optimal points, as they call it. And this involved that feedback loop, synthesize, get area latency throughput numbers.
Did it check if the changes broke anything?
Oh, yes. Functional testing was part of it. If the LLM introduced a bug with its changes, the framework would flag it, and the LLM would actually try to fix its own mistake.
Wow, okay. Debugging its own hardware optimizations. That's task one. What was task two?
Task two scaled up. It looked at optimizing the entire system, which might be made up of several of these kernels.
Putting the pieces together.
Right. The LLM had to choose the best configuration, the best area performance version generated in task one for each kernel in the system. The overall goal was typically to minimize the total system latency, but without exceeding a given total area budget for the whole chip.
So it had to make system-level trade-offs based on the kernel options.
Precisely. And for this, it had access to its toolkit, inspecting the code, using that ILP solver for system-level mathematical optimization, and running the full HLS synthesis.
Which LLMs did they actually use in these experiments?
They picked a couple known for reasoning, Deepseek R1 and OpenAI's O3 Mini. These are models that explicitly use that chain of thought approach.
Okay, the reasoning contenders.
And then they had a baseline for comparison, Deepseek V3, which is powerful but doesn't inherently focus on that explicit step-by-step reasoning style.
Got it. So the reasoning models versus a non-reasoning baseline. What were the results? Did the reasoning models shine?
Well, this is where it gets really interesting. The results were nuanced.
Uh-oh. Not a clear win for reasoning.
Not exactly. The reasoning models, Deepseek R1 and O3 Mini, they did have a higher success rate, meaning they were more likely to actually produce a functionally correct hardware design at the end.
Okay, that sounds good. More reliable.
Yes, but it often came at a cost. They generally took longer to run and used more computational resources. More thinking time, perhaps.
Makes sense. And the baseline, Deepseek V3.
It had a lower success rate overall, but when it did succeed, it tended to do so with the lowest computational cost. Faster, cheaper runs when it worked.
Interesting trade-off. But what about the quality of the final hardware? Did the reasoning models produce better chips, smaller area, lower latency?
That was the surprising part. The actual quality of the synthesized hardware, looking at the final area and latency numbers, it was pretty comparable across all three models.
Comparable. So the reasoning models didn't consistently produce better designs.
No, they didn't. In fact, in some cases, the non-reasoning baseline, Deepseek V3, actually found solutions with better area or latency than the reasoning models.
Wow. So the ability to explain its reasoning didn't automatically translate into better hardware design choices.
It seems not, at least not consistently in this setup. It suggests that the kind of sequential text-based reasoning these LLMs are good at might not map perfectly onto the spatial and parallel nature of hardware optimization.
That's a key point. Hardware is fundamentally parallel.
Exactly. Digging a bit deeper, Deepseek R1, the reasoning model, was best at meeting the target area constraint. It had the most runs that stayed within budget.
Okay.
But Deepseek V3, the non-reasoning one, actually achieved the lowest latency more often among those runs that met the area target. So different strengths.
It sounds like Deepseek V3 might have been better at optimizing for speed once the area constraint was met.
Possibly, yeah.
Yeah.
It suggests different internal strategies.
They also did a specific test just on task 2, the system level part, using an AES encryption benchmark.
Yes, they isolated that system optimization task. And in that specific test, Deepseek R1 did perform the best.
Ah, so the reasoning model was better at the system level part.
It seems so for that benchmark, which
Yeah.
suggests that maybe the quality of the kernel options generated back in task 1 really matters. If task 1 doesn't provide good building blocks, task 2 is handicapped, regardless of the LLM.
Right. Garbage in, garbage out, even for an AI. What about using that ILP solver tool? How did the LLMs handle formulating those mathematical problems?
That turned out to be a major weak spot. All the models, reasoning or not, really struggled with formulating the ILP problems correctly,
Struggled how?
particularly with modeling the latency. They had a hard time capturing how different hardware components operating in parallel affect the overall timing. It's that parallelism thing again.
They couldn't translate the parallel hardware behavior into the linear equations of the ILP.
Seems like it.
Yeah.
They could usually define the basic variables okay, but getting the objective function and the constraints right, especially for latency, was often wrong.
So a core hardware concept tripped them up.
Very much so. And interestingly, the non-reasoning Deepseek V3 seemed to compensate by just trying more things.
Yeah.
Its logs showed it doing way more synthesis runs and code inspections.
More trial and error, less reliance on getting the ILP formulation perfect.
That's what it looks like. It explored more directly through synthesis before resorting to the ILP solver.
The paper also gave some peeks into Deepseek R1's reasoning process since it provided those chain of thought tokens. What did that show?
It was revealing. The model could be quite verbose, sometimes seeming to overanalyze or get confused. It often ran synthesis just to figure out where things stood.
Like probing the environment because it wasn't sure.
Yeah. It explicitly acknowledged that latency modeling was hard because of parallelism, but then it would often fall back on overly simple, incorrect assumptions, like just adding up the latencies of sequential parts.
Did it show any flashes of actual hardware understanding?
It did have some moments.
Yeah.
For instance, it correctly figured out that if you use the same function multiple times in your design, each instance has to have the same hardware implementation. That's a valid hardware constraint.
Okay, so some grasp.
But then it would make weird choices. Like it might prefer a design that was slower and used more area just because a better design used too little area compared to the target budget.
Seriously, it penalized being too efficient.
It seemed fixated on hitting the area target, even if it meant worse performance. So the reasoning wasn't always, let's say, optimal from an engineering perspective.
And DeepSeek v3's strategy, again, was just more brute force exploration.
Pretty much. Lots of synthesis, lots of inspection. Try the ILP solver later if needed. A less cerebral, more empirical approach, maybe.
How does this work fit in with other attempts to use LLMs for HLS? Did the paper mention related projects?
It did. They mentioned projects like C2HLSC and HLS Pilot. They claim their agentic framework achieved better area results on some standard benchmarks compared to those previous works.
So an improvement in some respects.
Yes, the framework itself shows promise. But the main takeaway, the really striking thing, was that the advanced reasoning capabilities didn't give those models a clear edge in this hardware optimization task.
Yeah.
Unlike in software or math, where reasoning often leads to better results.
It really highlights that hardware design has its own unique complexities that current LLMs might not be fully equipped to handle yet.
Exactly. Which brings us nicely to our novel notion segment. Based on these findings, what kind of future research directions does this spark?
Yeah, where could this go next?
Well, given the struggle LLM showed with hardware specifics like parallelism and latency, my first idea is, what if we gave the LLM agent a dedicated hardware intuition module?
Hardware intuition, like a specialized part of the AI.
Sort of. Imagine training a separate, perhaps smaller model purely on hardware data, architectures, how pragmas affect timing and area, performance characteristics of different structures.
So a hardware expert system that the main LLM can consult.
Exactly. When the LLM is reasoning about a design choice, it could query this module to get a better, more grounded understanding of the likely hardware implications. Maybe using things like graph neural networks to represent the hardware structure, or even reinforcement learning trained on hardware simulators.
That makes sense. The paper showed LLMs lack this intuition. This could provide it.
Right. It directly addresses the gap identified in the research, the potential impact. Hopefully much more accurate and efficient HLS optimization driven by LLMs that actually get hardware better.
Okay, interesting idea. What's your second novel notion?
My second thought is about a hybrid approach. Maybe one single LLM trying to do everything, code rewrite, pragma insertion, ILP formulation, system integration, is asking too much.
Divide and conquer.
Kind of. What if the main LLM acts as the high-level strategist? It understands the overall goal, explores the main design choices, but it delegates the really tricky subtasks to specialized AI tools.
Like one tool that's really good at predicting latency for parallel structures.
Precisely. Or another AI tool specifically trained to formulate those complex ILP problems correctly for hardware. The main LLM would decompose the problem, hand off tasks to these specialists, and then integrate their results to make the final decisions.
Leveraging the strengths of different types of AI.
Exactly. The paper itself showed different LLMs had different strengths and weaknesses anyway. This hybrid approach could combine the broad strategic ability of a general LLM with the deep, narrow expertise of specialized AI components. It might be a way to overcome the limitations we're seeing with general-purpose models in such a technical field.
Both sound like really promising directions for future work. So wrapping up.
Yeah, the key takeaway seems to be that while using LLMs, especially in these agentic frameworks, shows real promise for automating parts of hardware design.
There are still significant hurdles. Understanding parallelism, accurately modeling performance, formulating complex optimization problems. These remain tough challenges for current AI.
Definitely. But it's important to credit the researchers for open sourcing their framework. That's a huge contribution. It gives other researchers a platform to build on and tackle these challenges.
Absolutely. It lets the community iterate and improve, which leads us to our final thought for you, our listeners, to ponder.
Given what we've discussed today, the promise and the current limitations, what kind of specialized training data or maybe totally new AI architectures do you think will be needed for AI to truly master the deep complexities of hardware design?
Something to chew on. It's clearly an evolving field.
For sure. And if you want to dive deeper into the specific study we discussed, you can find the link to the paper down in the show notes.
Thanks for joining us for this deep dive.